Hello everyone and welcome back to the channel. Today we are going over a problem with a cantilevered beam with a fixed end support and a distributed load, and we are going to look at again how to draw the shear force and bending moment diagrams. So without further ado, let's just get right into it. Alright, so as you've probably known in previous videos, shear force and bending moments are just practice, really. So you know what, let's just jump into the question. All right, so first we have to solve the reactions. Okay, the reactions, we have to at least identify them. So here we have AY, AX, and then moment around A, and we'll set that equal to the counterclockwise. It can be clockwise if you want, but just follow the sign convention, it'll be easier. Okay, next thing we got to keep in mind is the positive sign convention. I will draw it here again, but it should be ingrained in your memories by now. All right, so downwards, upwards. All right, remember, moments are the ones that's twisting, shear force is the ones going up and then down. Okay, and that just means that wherever you cut the beam, it's just positive. That direction, these directions are positive. Okay, always keep this in mind. So without further ado, I guess I should just discuss quickly what changes between, let's say, a point load and a distributed load. Well, the good thing about statics is that really all you're working with is these three equations back and forth. There's really no change in how you solve these problems, but we can just take a look. All right, there's a slight difference. So basically, we have this beam right now. It's 0 to L with a distributed load of W, right? And that's acting over the entire beam. First thing you want to do is, well, especially when you're not familiar with this, just draw a segment and analyze it. All right, so let's just say this is, I don't know, somewhere between 0 and L, right? Somewhere between 0 and L, right? Then you have this distributed load. Okay, it's still the same distributed load, and then you have the same reaction. So I'll just leave AX out of it because we know that it's 0. Right? Okay. So right now, if I were to ask you, okay, can you find this moment and this shear, right? What would you do? Well, you would do sum of forces, right? Sum of forces in the y direction, you know, just your usual stuff, equals 0, and then AY equals WX. Right? And you're like, sorry, AY minus WX, because AY is upwards, WX is, well, the distributed load times some distance between 0 and L, and that equals 0. Sorry. And minus V. V is this shear force, equals 0. Right? So V equals negative WX minus plus AY, right? Now you're looking at this and you're like, okay, what the hell does that mean, right? Well, it's unlike a point load in the last examples where by finding, like, let's say by cutting a point before or after a point load, you can just determine this value. What this basically means is that it's a function of the distance between 0 and L, right? So this shear force, if X were to increase, which means that if we move further along this beam, right, this whole thing would be more negative, and then therefore V would ultimately equal 0. All right, but that was a big jump. I know I'm not going through these as sequentially as I would like to, but let's say, for example, you should identify some critical points. How about that? Let's take that as a first step. So basically, what that means is you can identify what if we took a cut that basically at basically L equals 0, and what if we took a cut at the very end. Okay, we can analyze these 2 points and generally have a good idea of what we're looking at. So right now we have AY at this point, and if I told you, okay, what's this if there's practically 0 distributed load on this beam because you cut it so close to this fixed support that it's basically 0, right? Does that make sense? Okay, so basically V would just equal AY, right? And what is this AY value? Well, this AY value is just the reaction. So if you just solve for the reactions normally, you would have WL, right? Distributed load times the distance, right? So this point right over here, you would be experiencing this shear at WL, right? That's just the amount of shear force. Okay, so, and at the very end, now if we look at the very end, we can say, oh hey, oh shoot, we can say this distributed load, W, right? And then AY equals WL, right? And then finally, we have some shear force going down, right? So what would this be, right? If this distance is L. Well, it would just be, V would just be equal to 0, right? If we just do a sum of forces, WL going upwards because that's AY times WL, right? So WL minus WL is just equal to 0, right? So if we took a cut at this point, right, it would be 0, right? Okay, so we have these two points kind of figured out, and hopefully you followed me along just fine until here. Now you might be asking, okay, what about every other point in the middle? Okay, now we don't want to go and calculate every single point right in the middle. So what, and as you get more intuitive, more practice with these, you begin to develop, okay, just a pattern recognition, right? So these distributed load, to me, it would just be a straight line down, right? But obviously, maybe first time you're seeing this, you're like, okay, what the hell did you just do? I'll kind of explain it, right? So just going back a bit, you remember this equation we kind of figured out here, and we also figured out that AY was equal to WL, right? So let's just say we cut it at the end of the beam, right? X would then equal L, right? So this whole thing would just become 0, like this point we have here, right? And if we're cutting the beam at distance 0, or in other words, basically right at A, this thing would be WL, as we find here, right? So if you know anything about linear equations, right? If let's say we plug in x equals, if we just took a cut anywhere, right? If we just took a cut in the middle, right? L over 2, right? Minus W times L over 2 plus WL, right? So this would just be equal to positive WL over 2, right? So if we cut it at the halfway point, it would be somewhere here, right? So because this has no square or on top of anything like that, we can just simply draw, well, that was off the mark, but we can draw a straight line sort of like that. And all distributed loads without any shenanigans in between, like another load here, or maybe a triangle load on top, or multiple loads here, would generally have something like this. It's just a straight line down from one point to the other. All right. So now that we have that figured out, right, this is just your shear force diagram. Okay, and we can just take a shortcut. So what is the area under this curve, right? If this distance is L, and this distance is this force is WL, right? We can just say, okay, WL times L. Ooh, I'm trying to erase that. Okay, WL times L, right, divided by 2, or times 1/2. And that equals WL squared over 2. Okay, now what is this exactly? Well, just like the other problems, that's just the amount that it has to add up in the bending moment diagram. So how do we do that? Well, it's easy. First, find your MA. Right? It's always a good idea to actually just solve for reactions first if you know them. It makes your life a lot easier, but somehow I'm just very unorganized in this video and forgot to do that. So you have your MA, right? And then you have your entire beam, like so, right? So it's your W. This is W, okay? And then what is MA, right? W times L, that's the distributed load, total load, times L over 2, right? If we replace this with a point load and just add it at the midpoint, it would just be WL squared over 2, right? So, and since it's going, we set counterclockwise equals positive, right? This MA is spinning the system counterclockwise. So we need a clockwise moment to balance that. And that equals WL squared over 2, right? And since we set counterclockwise as positive, we must set this as negative, all right? So I know this is a bit confusing at the beginning with all these switching around between positives, negatives, counterclockwise, clockwise, right? But just remember, at the end of the day, your thing is not floating through space, and that's what we're trying to achieve. And you have this positive sign convention, so just stick with it, all right? Stick with the sign convention, nothing is floating through space, you'll be fine. 3 equations, you're going to be using these a lot, all right? So, finally, we know that since this area from 0 to L is W squared over L, right? And this is W squared over L, right? This area under the shear force diagram just means how much we have to increase or decrease on the bending moment diagram. Right? So if from 0 to L we have a total increase, nothing in between, no changes. Whoops, I'm getting ahead of myself actually. If we have no changes, right, we can just add a WL squared over 2 at the very end. So at L. And then this is 0, right? So my question to you now is, what does the line look like in between here? If you ignore the last 20 seconds in the video, what would the line look like? I'll give you a second. Just pause the video, try to think, right? If you're just adding the area and then just making that a sort of line or curve, anything, what would it look like? Okay, so right now, if we think about this, right, this is a triangle, right? And if we were to add this area, right, at any point, so if we were to take a chunk, any chunk of this, and that is how much we added to this, right? So basically, what I like to think is that since this is a positive area, always remember, okay, above the shear force diagram is always a positive area. And it increases this value, right? So it wants to add on top of this video. That's how we ultimately get to 0 on this point, okay? So this area would increase it by a certain amount, right? So let's say until maybe here, right? And this chunk would probably increase it a bit less, right? This chunk, maybe a bit less than that, right? And finally, this chunk, maybe a bit less than that, right? And obviously, we don't want straight lines in the middle because we can take a cut really anywhere. It doesn't have to be where I cut it, right? But if you think about just adding these areas up and just adding that to this value at WL squared over 2, right? That's how we increase the bending moment. And we have this curve. Maybe that was not the best curve, but it looks something more like this, okay? Because we are just simply adding the area under the curve like we did for the problems in the previous videos on the shear force diagram to the bending moment diagram, and that's how we get this curve. Because it's a triangle. It's not a steady, if this was a rectangle, it would be a straight line. Something like that, right? Because it's a steady kind of, like no matter what rectangle you add up, it will always be the same amount, but that's not the case for the triangle, right? Hence, there will be a curve, all right? Now, do you need to know exactly what every point on this curve, the values of every point on the curve is? Chances are no. No, you really don't. Until we get to more complicated problems where there will be point loads in the middle or maybe moments applied where you'll see like sort of jumps and dips and all that fancy stuff. And even then, you only need to identify at the critical points, which is, usually start, end, or where an additional force somewhere in between is applied. All right, so yeah, a bit messy. Today's video was also a bit longer than usual, but I really hope that this helped. And of course, if you're ever confused, just leave a comment in the comment section. I'll be looking. It's not like I have many views anyways, so there you have it. Yeah, I hope this video helped, and I'll see you in the next one. Bye-bye.